Hi guys. In this video I'm going to talk about the work energy theorem, and I'm going to show you the applications of this work energy theorem. So I'm going to do a couple examples, maybe 2 or 3 examples to get the point across. So the work energy theorem is basically a very simple concept. It's a very simple idea. It just tells you that if you have some energy initially, okay, and if there is some work done, okay, on the system, plus any work done by any external agents, external forces, well, that's going to change your energy level. That's really what it means, okay? And so a lot of times it's written as like the work done by external forces is the change in energy. In other words, if I move the EI to the other side, it will become EF minus EI, which is basically the change in energy. And here when we talk about energy here, we talk about all the forms of energy: potential, kinetic, potential, the elastic potential, the gravitational potential, and your kinetic. All right, so let's do an example here, and I'm going to start with something simple. So let's say I'm going to drop an object that has a mass of 2 kilograms from a height of, I'm just going to pick a number, 10 meters. Okay, and I want to figure out, well, with what speed is he going to hit the ground? Now we've done this with kinematics, but I think the work and energy is much quicker. So let's see what we have here. I'm going to think of this position here as my initial position, and this is my final position. And I'm going to say that in between them, there is no friction. So for now, we start with no friction, and I'll just add friction to that. Well, I'm going to look at what kind of energy I have up here. If I start this from rest, the only thing I have, and if I use this as 0 for gravitational potential energy as the reference, all I have here is gravitational potential energy. So I have mgh plus, well, if there is no friction here, there are no external forces doing any work. So plus nothing equals, when I'm all the way at the bottom, I'm at the reference for gravitational potential energy. So there is no gravitational potential energy. And I have kinetic energy because the ball is moving right at that moment. It's going to hit the surface. Okay? And then I can find the speed with which it's going to hit the table or the floor. So as you can see, the mass is not even important here. Okay, so this is 10 times 10 for the 10 for g and 10 for the height equals half times v squared. And you can solve that equation, and you get v equals square root of, it looks like it's 200. And so it should be about 14 and change. So let me just take out my calculator and do it exactly. So we do square root of 200. So it's about 14.14 meters per second. Okay. Now let's throw in friction on top of this. Okay, let's say this time they say, you know what? As it's falling, there is some air resistance. So the force of air resistance, so I'm going to call it F air. It's another form of friction. And the average, let's say it's about 10 newtons. Too many tenths. So I'm going to say 8 newtons. Okay, and we have to figure out with what speed we're going to hit the floor now. Well, it's going to be energy in the initial position. So I don't have anything here. No kinetic, I mean. I have just gravitational. If I throw it down, it's a different story. Then I'll have to add the kinetic up there. Plus the work done by friction, okay, equals, well, what kind of energy do I have down here? Well, I have 0 gravitational potential, so I have just the kinetic energy. So we cannot cross out the mass at this point. So I have to keep it. So it's 2 times 10 for the g times 10 for the height. Now the work done by friction is the force of friction times the distance over which this friction is acting, so which is basically 10 meters. And the friction is acting up while the object is moving down, so there is a cosine of 180. I'm just using the work formula. Equals 1/2 mass times v squared. And our speed obviously should be less than what we had earlier. So this is basically 200 minus 10f, because the minus comes from the cosine of 180, equals v squared. Well, the f is 8, so I'm going to put that as 8. So it's 10 times 8. So what is that? 120 equals v squared. And v is close to about 11 meters per second, because 11 squared is 121. All right, so let's do another example. Okay, so let's say I have an object that's sliding on a surface that has friction. Okay, and I want to figure out how far is it going to go before it comes to a stop. Now, we did this with the forces. I think we can try it with the energy and see, and you decide what's better. So let's say this has a mass of 4 kilograms. Okay, and I'm going to say the coefficient of friction here, kinetic friction, is maybe 0.1. Okay, and that's all I have. And here it's going to stop, and here initially it's moving at, let's say, 10 meters per second. Okay, so in here I'm not even going to talk about the concept of gravitational potential energy, because this is on a leveled surface, and I'm going to pick this as my reference, right? So it doesn't really matter. It's the difference in potential energy that matters. So here I have, so energy initial plus work external, and you can see that there is friction here. So friction is going to do some work on this block, equals energy at the end. Okay, now I have kinetic energy in the beginning, 1/2 mv squared plus, well, the work done by friction is the force of friction times the distance. Now, if the object is moving to the right, friction is acting left. So there is a cosine of 180, which turns out to be negative, equals, now let's see what we have at the end. There is no gravitational potential, and there is no kinetic because it came to a stop, so we put a 0 in there. All right, so this is going to be 1/2 times 4, and by the way, you could do this without even knowing the mass, but we'll do it with the mass. So 10 squared. Now we have to figure out the force of friction. Now, force of friction is mu Fn. Okay, and Fn in this case, this is Fn, this is mg, is mg. So it's mu times mg. This is mg. So I'm just going to put in some numbers. And you can see that even if I didn't have the mass, the mass will cross out. So 0.1 times 4 times 10. So that looks like it's 4 newtons, right? So plus 4 times d times -1 from the cosine of 180 equals 0. And we'll just solve this. So that's 100 times 2, that's 200 minus 4d equals 0. And you get a d equals 50 meters. Okay. Now let's do something that's on some kind of ramp. All right. So I'm going to do something like that. Okay. So I have a block here that I'm going to actually give it a kick. So I'm going to kick it at 2 meters per second. And well, let's do 10 meters per second. And it has a mass of 2 kilograms. And I want to figure out how fast it is going when it's at the bottom of the ramp, if there is no friction. All right, so I'm going to look at this as my initial state, and this is my final state. So initially, I have gravitational potential energy because I'm elevated. Okay, I'm using this formula here. Okay, do I have kinetic? Yes, because it's moving at this level, plus 1/2 mv, well, initial square. Okay, now if there is no friction here, okay, there is no external work, so there is nothing there for the work, equals, well, all the way down here, if I choose this as 0 gravitational potential energy, I only have kinetic energy, 1/2 mv final square, final basically at the bottom. You can see that the mass crosses out here too, so we don't even have to bother with the mass because it exists in every term. So this is going to be 10 times 10 plus half of 10 squared. Too many 10s, right? Okay. No, I don't have the height here, actually. No, I have to give you the height. So I could give you the angle and the length of the ramp, or I can just give you the height. So I'll say 5 meters equals half V final squared. So 50, this is also happens to be 50, so that's 100 times 2. So VF is going to be about 14.14 if my math is correct. Okay. Now let's throw in some friction now and see what changes. And even with friction, the mass shouldn't matter, but we'll do it with the mass. So if we have friction, I'm going to give you the coefficient of friction here as being 0.1. So I'm going to say mgh, because it's elevated, 1/2 mv squared, because it's moving initially, plus work done by friction, equals, well, what do I have down here? I only have kinetic energy at the bottom. Okay, so we're going to start, so we have to figure out the work done by friction. So the work done by friction is just the force of friction times this distance here. So I need to know this distance. So basically, maybe if I give you this angle here, you can figure out that distance, the length of the ramp. So F times, this is D here, and we can figure that out easily. Cosine of 180, because as the object is moving down the ramp, friction is in the other direction. Okay, so let's figure out the force of friction. So if we are on a ramp like that, force of friction is this way. I'm giving you the coefficient of friction, so we have to kind of like use this formula. Force of friction is mu times Fn. The tricky part is to figure out Fn. Well, okay, so these are the components. So this is the F perpendicular, if you remember this from the inclined planes, right? This is the F parallel, and this is the Fn. And this F perpendicular, if you remember, it was just mg cosine of the angle. Okay. And F perpendicular is the same as Fn. So this force of friction is going to be mu, which is 0.1 here, okay, times Fn, which is F perpendicular, because the block is not moving this way. So that's going to be mg cosine of 30. And so I'm going to do the numbers. mg, right, cosine of 30. Okay, so the force of friction will be, let me do that quick. So what is that? That's 20, that's 2. Yeah, that's 2 cosine of 30. So it's 1.73. Very little friction. So I'm going to come here and say this is 2 times 10, a height of 5, plus half times 2. The initial velocity is 10. We're going to square that. Force of friction is 1.73. This distance here, I think if you work inside this triangle here, or what looks like a triangle, that should be a 10, because sine of 30 is 5 over d. So d is 5 over sine 30. So this is a 10. A lot of 10s. Cosine of 180 is -1, so I'll put a negative here, equals half times 2 for the mass, V final squared. And it should be less than what we found earlier. So let's see what we got here. 20, that's 100. Okay, this is another 100, minus 17.3 equals V final squared. And you can solve that equation, and you should get a V that's less than before. All right, and all right, let's look at an example maybe with a spring. Okay, so I'm going to take this spring here. Let's say this is the unstretched position. Okay, let's say it's stretched. I stretch it 2 centimeters. Okay, and I want to stretch it another 3. So in other words, This is the unstretched position. Okay, it's stretched. If I stretch it 2 centimeters, and then I stretch it again from this position here. So it's stretched 5 centimeters. Okay, so I want to know how much work was done to stretch it from 2 to 5 centimeters. So let's try that. So initially, the spring has some energy. It has some elastic potential energy. So 1/2 K X initial square. Is there any work done? Absolutely, because I was the one doing the work. I applied the force over some distance, plus the work done by Mr. E, okay, equals, and at the end, the spring is stretched more, 1/2 K X final square. Now, I have to give you the spring constant. So I'm going to say the spring constant is 20 newtons per meter. So it's going to be half times 20. Now, initially, it's stretched 2 centimeters. Change that to meters. Plus the work done by Mr. E equals half times 20 times the final position is, from the beginning, is 5 centimeters, right? And you can solve that equation and you would come up with your the work that I did to stretch it from 2 to 5 centimeters. And that should do it. So thank you for watching.